Hi, my name is Ron Lohman. I'm here with my colleague Graham Allen, and today we're going to talk about memory interfaces and their impact on AI chipsets. With the advent of neural network accelerators, memory is one of the major challenges with respect to bandwidth, capacity, and power consumption. Can you talk about maybe some of the technologies that address some of these?
Absolutely. There's a tremendous number of memory technologies coming online in order to specifically address some of the requirements of the artificial intelligence market. So the one that comes to mind first is the high bandwidth memory, which is a new JEDEC standard, which actually, in order to have higher bandwidth, you can go wider or you can go faster. And with HBM memories, it's about going wider. And they're doing it in a unique way because you can't do it on a PCB. It uses 1024 bits per interface. So you actually have your silicon chips and the silicon DRAMs go on a second piece of silicon, which is called an interposer. And by connecting those up using through-hole silicon vias, you can actually have a very compact system, operates at very high speed, and is very power efficient as well.
Okay, yeah, so we see these on a lot of AI accelerators, maybe 2 instantiations, maybe more. What's the roadmap look like for HBM?
Well, the roadmap is it's going to stay about as wide. There's going to be more channels within that same width, the overall width, and the speed for HBM3, for example, speed will probably double from about where it is today for HBM2.
So the bandwidth obviously has a really nice roadmap to continue to increase over time. How does it compare to maybe some other technologies that are out there like GDDR?
So GDDR6 is the current generation today. It is a graphics memory. It has a very, very high interface speed for a traditional DRAM on PCB application. So it doesn't need the interposer. It doesn't get to the same bandwidth as HBM, and it doesn't have the same power efficiency. You were asking about power before. HBM has a very low power efficiency, which is the amount of power that it takes to transmit a bit of data, because it's not a terminated interface, and it doesn't use a PCB. It uses that very short interposer, so there's not much capacitance that's being toggled back and forth.
Okay, so the big advantage is really in energy or in picojoules per bit. Yeah.
Yeah.
Okay, so so that really kind of addresses a lot of the bandwidth constraints that we see with AI chips. What about capacity? We see these huge models up to billions of different parameters or coefficients that we have to store. What do we see on the capacity side?
If you need high capacity, you need the good old DDR4, DDR5. DDR4 is available today. DDR5 is coming online. It's being designed into systems today, and it's really the only DRAM protocol that is designed to work with really large numbers of individual DRAMs. You've got registered DIMMs with 3D stacked DRAMs on them that can get you today 128 gigabytes of data on one DIMM, and you can pop 16 of those DIMMs around an SoC if you wanted to.
Okay, and then the final thing is power consumption. And so traditionally LPDDR has been put in mobile phones, and we're seeing in automotive. What can you say about the LPDDR?
LPDDR is a very interesting technology because it was designed for mobile phones, but it finds a ton of applications outside of that space. Yeah. And people think of it as low power because the LP part stands for low power, but it's really only low power when it's not doing anything, which is why it's used in mobile phones. Most of the time they're not doing anything. You don't want them draining your battery. The AI applications that don't need so much bandwidth or capacity, LPDDR4 or 5 is a great option because it's cheap. It's cheaper than the other memories we've talked about, and it's relatively friendly to put on a board and widely available.
Yeah, so we've seen LPDDR, it looks like, in a lot of designs for traditional mobile, but maybe even to some of these edge computing designs where they want to lower the power consumption specifically for AI algorithms.
Yeah. Okay. But again, if you're pumping at maximum data rate, it's not a ton lower power.
Okay.
It's designed to be lower power when it's not doing very much.
Okay, interesting. Is there anything else that Synopsys does it's not just a memory interface, what else does Synopsys do to help customers in their designs?
One is with HBM, we can offer them a reference interposer.
Okay.
So because the microbump array is predefined for an HBM interface by the JEDEC standard, and we match that with the PHY in order to have straight interposer routes, it's pretty much plug and play, ready to go out of the box. For the DDR5 and the LPDDR5 options, we have an online PHY compiler tool, which customers can use to answer the questions, how big is it and how much power does it consume? Because they always want to know what area on their SoC and power consumption. And finally, we have a product called Platform Architect, which from the controller perspective, customers can use to discover how the controller can be modified through the programming capabilities that it has in order to optimize its bandwidth utilization for their specific traffic patterns.
Yeah, and I see a lot of potential in that. Obviously, these AI algorithms, some of customers are doing second, third generation designs and playing with the architecture. So this type of tool can go ahead and modify these parameters to optimize for these things.
Exactly. You're basically just modifying the configuration registers to prioritize traffic in various ways to optimize the throughput for your specific traffic patterns.
I want to thank you for sharing your expertise with us today. And it's an exciting space, and 2020 will look like a lot of new AI chipsets with different types of memory interfaces. Thanks.
My pleasure.